I'm Anil Kumar. In this series, we'll discuss higher order derivatives. I'll share most of the concepts which you need to understand for higher order derivatives. So we'll begin with very simple example, derivative of derivatives, and we'll talk about the function 1 over x. Major application in this chapter is about relating displacement with velocity and acceleration. As you know, velocity is first derivative of displacement and rate of change of velocity is acceleration. So acceleration is derivative of velocity or second derivative of displacement. So that is derivative of derivative. We'll take up a simple example, displacement being represented by 1 over 3t cubed minus 2t squared plus 3t. We'll graph displacement, velocity and acceleration and see how we can answer questions like this. Example, when is the object at rest? When does it change the direction? When will it return to its initial position? When is it speeding or slowing down? So let's first begin by understanding derivative of derivatives. So I've taken a very simple function which is 1 over x. Now what is the derivative of 1 over x? Well, it is minus 1 over x squared, right? You could write this as x to the power of minus 1 and then figure this out. Now, what is the derivative? Second derivative, I will say, derivative of derivative. That means, what is the derivative of minus 1 over x squared? Well, x to the power of minus 2, that minus 2 when multiplied by minus 1 gives you plus 2, right? So what you get here is 2 over x cubed. Now if we continue this process, then the next derivative will be negative 3 times 2 x to the power of 4 in the denominator, and then the fourth derivative will be that goes in the top with a negative sign which makes this positive. So we have plus 4 times 3 times 2, right, over x to the power of 5, and the process actually continues. So for a function like this, we may have any number of derivatives, correct? So in general, we could write nth derivative of this particular function as, you will notice here, that for fourth derivative, denominator had a power of 4 plus 1, right? So it should be x to the power of n plus 1. In the numerator, we have terms like 4 times 3 times 2 times 1, right? So which could be written as n factorial. And the sign here really depends on which derivative you are taking. If it is even, it is positive. If it is odd, it is negative. So we could write minus 1 to the power of n to take care of the sign. Do you see that? So there could be functions for which we may go on and on finding derivatives. Now let's take another kind of function which is, let us say, f of x equals to x cubed. Now a polynomial with degree n will have limited number of derivatives. As you know, first derivative of this function will be 3x squared. The second derivative of this function will be 3 times 2, 6x. Then the third derivative for the function will be just 6. And what is going to be the fourth derivative? Well, the fourth derivative for this function is going to be 0. So what you really see here is that for a polynomial, if n is the degree, then we can at the most go for n plus 1 derivative. Each time you differentiate a polynomial, its degree decreases by 1 and derivative of a constant is 0. Perfect. Now with that in mind, let's continue and explore few applications. One of the major applications is definitely talking about displacement, velocity and acceleration. To describe the scenario, I've taken a very simple example. Simple in the sense that we can easily factor the function itself and its derivatives, right? So let's move on. While finding derivative of this function, we'll also talk about all these topics mentioned here. So the function here is displacement function s of t equals to 1 over 3 t cubed minus 2t squared plus 3t. Let us assume that displacement is in meters, right? Let's say this is in meters, and time is in seconds. And let us also assume that time t is greater than or equal to 0 and t is in seconds. Okay. So the given function to us is displacement s of t is equals to 1 over 3 t cubed minus 2t squared plus 3t. The derivative of this function is going to be 3 times 3t, 3 cancel, so we get t squared minus 4t plus 3, and the second derivative of displacement will be 2t minus 4. Correct? Now, as you know, from the rate of change which we learned earlier, derivative of displacement is also known as velocity, right? So we could write this as velocity, and rate of change of velocity is acceleration. So second derivative of displacement is actually acceleration, right? Now, these three are very much related as one of their rate of change. That really means that if I sketch the displacement function, then slope of tangent is going to give me velocity, and slope of velocity is going to give me acceleration. Correct? Units for displacement, the units will be in meters. Then for velocity, it will be meters per second. As far as acceleration is concerned, the units will be meters per second square, since we are differentiating with respect to time, right? So these are the units. That is how the units are related, right? Now, let us try to sketch these functions and explore the whole situation. So let's look into the displacement function itself. I could write this as taking 1 over 3 common. I could write displacement, let me write here, displacement as equal to 1 over 3. We can take t common, right? So we are left with t squared. So if I have taken 1 over 3, I get 6t inside with minus sign. And here 9 with plus. Correct? We could factor these and write it as 1 over 3t. And what we get here is t minus 3 whole square. Perfect. Now that gives you an idea that we could sketch this cubic function with two zeros. One at t equals to 0, the other one at t equals to 3. And the 0 at 3 is, let me just sketch it here. So we'll make a not very precise but kind of working graph so that we understand the concept. We are also assuming that t is greater than or equal to 0, so we'll only sketch the right side. Is it okay? So we have a 0 at t equals to 0. As the value of t increases, it will increase first and then it has to turn, since we have a 0 at minus 3 also, right? Which is a order 2 0. So the function expected is kind of like this. Correct? So that is how the function is going to look. Where this is 0 for us, we are talking about s of t with time t, and this point here 0 at t equals to 3. So that becomes the displacement graph, a polynomial of degree 3. Now if we look into the velocity graph, it is t square minus 4t plus 3. Let me rewrite this. We have velocity as the derivative of displacement. I can factor this also. T square minus 4t plus 3 can be written as t product of 3 and 1 will give me 3, and sum both negative will give me minus 4. So it is t minus 1 times t minus 3. So the velocity graph, if I want to sketch here, it will have two zeros. One zero will be at t equals to 1, the other one at t equals to 3. From the given situation, that is the graph of displacement, what do you notice? Velocity is basically rate of change of displacement. You can see from here that turning points result into zero velocity. So this turning point should be at 1, right? It is not to the scale. And the other turning point is going to be at 3, which will coincide with this particular value. Correct? If I substitute t equals to 0, I get 3. Okay, so we can actually find those values also. Now, I'm not bothering about the scale so much, but we are more concerned about the nature of the graph. But anyway, if I take a value which is kind of 2, then 2 minus 1 is positive 1, but this is negative 1. So that gives me negative 1 as the value, right? So we get a negative 1 value, and for t equals to 0, we get positive 3 value. Okay, let's say this is positive 3. Since I have a lot of things written here, so we'll just restrict ourselves. Okay, so let me sketch this graph here. We'll go like this. Okay, let's say this is the velocity graph in green. And that point will say minus 1. Okay. So we get a velocity graph from here. And now let's talk about the acceleration. Acceleration, as you see, is a linear function. 2t minus 4. So if t is 0, minus 4. And this function is going to be 0 when t equals to 2. So somewhere in between, we expect this function to be 0. So I'll just kind of draw a line, okay, like this. Right? So starting from here. So that becomes the acceleration part. Is it okay? So now we have all the three represented on one graph, and obviously the y-axis is different for all the three. Well, their plus and minus 3 or 4 values are not going to match. But with time, which is same for all three, what we notice here is that the displacement increases, then decreases, and then increases, right? There are two places where the value is 0. This point here, when the object returns to a displacement of 0, we say is a point where the object returns to its initial position, which is 0. You are getting my point. Is it okay? Now, there are a few terms which were introduced to you initially, and now we'll talk about them. Terms like when does the object returns to initial position. So let's talk about this. Return to initial position. When the object returns to initial position, it really means that the displacement is the same as the displacement when t is 0, because the object started at 0. Is that okay? So in our case, s of 0 is, if I substitute 0 here, is 0, and we have a function written in factored form, which is 1 over 3 t times t minus 3 whole square. So we see that at t equals to 3, again the position displacement is 0. So at t equals to 3, the object returns to its initial position. You get an idea, right? So this is one technical term which we will be looking into. Another term which we need to understand is about the objects changing direction. So first we'll consider when is the object at rest. Rest means that the velocity is equal to 0. Perfect. So from this graph, which we have also drawn from this equation, we know it is at rest at these two positions, that green curve. So we know t equals to 1 and t equals to 3 is when the velocity equals to 0. So that is where the object is at rest. Is that clear? Now let us try to see how to answer the question, which is about the direction of movement. So when is the object moving away from origin? So we say direction. So in direction we have two terms. When does the object move away from origin? If you are moving away from origin, in that case the displacement is increasing, correct? So in this diagram you see that from 0 to 1 the object is moving away from the origin, correct? And then from 1 to 3 it is moving towards the origin since the displacement is decreasing. So from the displacement graph shown in pink, you can make out that the object is moving away from origin in the interval 0 to 1, right? And then in the interval 3 onwards. Let me write 3 to infinity. And in these intervals, what do you notice? You also notice that in these intervals, velocity is positive. So direction is away from origin when we have two things in common. And that is the velocity v of t is actually, see, 0 to 1, it is positive. And then from 3 to infinity, also the velocity is positive. So velocity is greater than 0. In that case, the object moves away from origin. Correct? So if object is at rest, then the velocity is 0. And if velocity is greater than 0, that means positive, object is moving away from the origin. If the velocity is negative, in that case, it moves towards the origin, as you can see here. Perfect. Now let us explore higher order derivatives with the help of graphs. Derivative basically is a slope of tangent line on any curve. So here we are given a curve. Based on this curve, we are going to answer all these questions, right? The question here now is, the object moves in a straight line, its position s of t to the right of a fixed point is given by the graph. When does the particle return to the initial position? B. When does the motion of the particle change direction? C. When is its acceleration positive? D. When is the object speeding? E. When is the object slowing down? So let's answer these questions one by one. The very first question here is, when does the particle return to initial position? Now initial position means at t equals to 0, what was the position? So at t equals to 0, the position is 0. So we can say that s of 0 is 0. Now looking at the graph, when does it become 0? Next time. So we can see from the graph that at t equals to 6, s of 6 is also 0. That means that particle returns to initial position at t equals to 6. correct? So that is how you can read it from the graph straight away. Question B is, when does the motion of particle change direction? Now initially the particle is moving away, as you can see here, from 1 to 2 till this position. Displacement is increasing. So at 2, displacement starts decreasing. So this is the portion when the direction changes. So it becomes from going away to coming closer. So that is one point. T equals to 2. So we can write T equals to 2 is one point. In this case, the direction changes from going away to coming closer. And then again at 6, we notice that direction of the movement changes since the displacement, which was initially decreasing, starts increasing. So the other time is T equals to 6. Now at 6, displacement, which was decreasing earlier, is now starts increasing. Do you see that? Part C is, when is its acceleration positive? Now that is a difficult question to answer. Before asking or before answering question about acceleration, we need to sketch the graph for velocity, correct? We have answered 2 questions which were related to velocity. Now what we are going to do here is we are going to sketch graph of velocity from the given function. So we'll try to sketch graph of velocity from the graph of displacement. Now turning points means that the tangent is going to be horizontal. Perfect. Horizontal means slope is 0. So at this point, velocity should be 0. At 6 also, velocity should be 0 since the tangent at this point is horizontal. As you can see from the curve, s of t is kind of a cubic function. So what we note here is that s of t is cubic. So the velocity, which is the derivative of displacement, is expected to be quadratic. With these two zeros, and we also know one thing, that in the first half, or rather from 0 to 2, the tangent is positive. Do you see that? So here the tangent is positive. It is increasing. That means velocity is positive in this portion. Since tangent is negative in this portion, velocity should be negative. Combining these two informations, that we have zeros here, a quadratic function, we could actually sketch a graph which is kind of like this, of a parabola. Clearly, between 2 and 6, 2 plus 6 is 8, divided by 2 is 4, we should have minimum, right? So that is the point where we do have minimum for the velocity. So the function sketched in this color pink is basically that of the velocity, correct? Now we'll check our answers with respect to velocity also. When does the motion of the particle change direction? It changes direction when velocity is 0. As you can see, velocity changes from positive to negative. That means earlier the object was going away, now it is coming closer. At this stage, velocity is changing from negative to positive, means the object is coming closer, moves away. Perfect. So it matches with the description also. Now let's talk about acceleration. How do we sketch acceleration from the velocity graph? Acceleration is derivative of velocity. Since there is a turning point here, it leads to a 0. Second, acceleration should be a linear function. Is it okay? In the first half, that is from 0 to 4, the tangent to the curve is negative, right? So that means acceleration will have a negative value before 4. So I could make any negative value here and join this point with a straight line. So this line indicates acceleration. Do you get an idea? Just by knowing 0, we at least know that acceleration is going to be positive on the right side of 4 and negative to the left side. And so, since it is represented by a straight line, we can just draw a line and answer rest of the questions. Do you get an idea? So now let's answer part C, D, and E. Part C is, when is its acceleration positive? So clearly, acceleration is positive after 4. So we can write this as from 4 after 4, right? So since there is no restriction, we'll just say 4 to infinity. Part D is, when is the object speeding? Now that's a very interesting part. We have to first understand, when does object speed? Now speeding is the case when both acceleration and velocity when multiplied should be positive. That is to say, if acceleration times velocity is greater than 0, then the object is speeding, and it is slowing down when the product of acceleration and velocity is less than 0. So basically, we have to now consider the points where both are positive or both are negative for speeding. So let's draw a few lines which can help us. So these are the zeros for the velocity, and now let me draw 0 for acceleration also. As you can see, from 0 to 2, velocity is positive, acceleration is negative. That means the object is slowing down. So in this portion, object is slowing down. But from 2 to 4, both velocity and acceleration are negative. That means they are speeding. From 4 to 6, acceleration becomes positive, velocity is still negative, so it is slowing down. And after 6, both are positive, so it is speeding. So when is the object speeding? Object is speeding in the interval from 2 to 4. And after 6, we can write 6 to infinity. When is the object slowing down? It is slowing down between 1 and 2, when both velocity and acceleration have opposite signs, and between 4 and 6, and between 4 and 6. Do you get the idea? So if you are given the graph of displacement, then easily you can sketch graph of velocity as well as acceleration and answer all such questions. So I hope with this you have fairly good idea about how to find derivative of derivatives if you are given algebraic equation, and how to work when the graph is given to you. Now in the next video, I'll take a few examples where we'll calculate different values and sketch more accurate graphs. With this, I hope you get fairly good idea about the topic, higher order derivatives, and how displacement, velocity, and acceleration are related. Feel free to write your comments, and if you like and share my videos, that'd be great. Thank you, and all the best.